How are you? Are we good?
We're good.
Okay. So if I have a box with some boxes in it, and then they're doing some stuff, who knows what, and then there's another box with some boxes in it, and they're doing some stuff, who knows what, and then these are connected in a larger wiring diagram. I don't know, maybe this one comes through and goes like that. Then this is 3, then what we have here is like phi1 taking p11 tensor p12 to q1. And there's q2, and there's this big thing is r, and there's p21, p22. And you don't have to be able to read this because I'm just kind of like, you have to be able to read the basic shape, but you might not be able to read this in there. But hopefully you understand like why I'm writing what I'm writing now. Any questions about why what we have in front of us there is this sort of stuff? Okay. Any questions on this? This is what's in front of us. We have psi doesn't know what's going on in these two boxes. It's just working with, adder circuits. Whereas, inside this adder circuit's a bunch of logic gates or something. Okay, so that's what's here. And our goal is, well, first of all, we want to get a big wiring diagram where like you get to see that your computer really is made of logic gates. You don't have to think of it as adder circuits if you don't want to. Usually you want to do the factorization. You're happy to have it. But if you need to, you can drop all the factorization and see yourself as just a bunch of like quarks or whatever if you really want to get there. Doesn't help you much, but maybe it's true. In this picture, it is true because this is the picture of it being that way. So what would you do to get a big wiring diagram where you didn't know about the Q's anymore? You just knew about the P's inside the R. Compose, okay, what's the type of the composed thing?
If you didn't know about the Q. So
yeah, like so kind of like if I have a map from A to B to C,
yeah.
and I want to compose, then like F composed G goes from A to C without really remembering anything about B.
Wouldn't you ignore? Yeah.
Yeah.
So you're gonna.
Okay, so what do we do?
Yeah, so the phi 2 is 2, 1.
P1, P.
Did I mess up?
P21, tensor P22, tensor P23, right?
So what are you saying to write?
Sorry, it's for the phi 2. The first
Oh.
one
Thank you.
2,
Yeah, thank you. Good catch.
Just tensor everything together.
Okay, so what's the input type?
So
Thank you.
yeah.
And we're trying to get from that to R. Okay, so how do we do it? Well, phi1 tensor phi2. Like when you have a monoidal structure, you can not only tensor objects, but also morphisms. So phi1 is a map from these two to q1, and phi2 is a map from these two to q2. And then we can just hit it with psi and get to R. And this will be, you can, whatever you did, if you were like trying this on paper in your own case, you'll get the thing that you're expecting. This will work. Okay, but what if we had dynamics in each of these? So we had S11 y to the S11 mapping to P11. S11 looks complicated, but it's just a single set called S11, right? So this is a little coalgebra or a machine running inside of here. And then someone else gives us S12 y to the S12 mapping to P12. And they gave us all 5 of them, S21, S22, and S23. So for each of these 5 boxes, they gave us some dynamics. Then how in the world would we get dynamics for R?
We're going to have another layer in that.
Yeah, it's actually super easy. If we S11 y to the S11 tensor dot 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 tensor S23 y to the S23. But that's not dynamics yet, because for dynamical systems we need sy, ty to the t. So what is t? Like what's the
Oh, so you just do S11 S. So the coefficients or the positions are S11, S12, S21, blah blah blah, and then the y to the same thing.
Yeah.
Yeah. You're just tensoring all the.
I'm just tensoring
Yeah,
those
or
all together.
multiplying.
Multiplying.
Yeah.
These are isomorphic, and now this. So what is this saying? It's saying that the state of this big machine is just keeping little local states in all 5 places. Each one of them is managing their own state, and these are just running in parallel. So the parallelism, if you had like some parallel capacity with your processor, this would tell you exactly how to keep all of that managed. Yeah. Okay. Questions about this? This is how you turn dynamical systems inside into dynamical systems outside, how you compose wiring diagrams, etc. And they didn't really need to be wiring diagrams. They could have been very fancy things that added numbers and did all sorts of stuff. But yeah.
One thing that I've been struggling with since encountering this is, I'm going to try to verbalize it. So here we have, before we put in the dynamics, we have a sort of syntax.
Yeah.
We heard the comments earlier. It's kind of describing the holes in which we're going to put these dynamical systems.
Yep.
And then we put in these dynamical systems, but in both cases we're dealing with polymaps, like the sort of bubbles, as Sophie called them in one of her talks, into which we put them are described with polymaps. The dynamics are described with polymaps, and I'm trying to square that with this notion of separation of syntax and semantics, and involving a mapping into a syntax category into a semantics category, and I'm struggling with like how to make sense of it.
Yeah, I mean, it sounds like you're saying we have syntax for wiring diagrams, and we have syntax for filling in the bubbles.
Yeah.
And if this is to be some kind of operad, and algebra, then these pictures are like giving us how the operad works.
Yeah.
And then these pictures are giving us how the algebra works,
Right.
like what you can actually pop into the bubbles.
Right.
And usually those feel like they should be separated, but here they all just feel like the one thing.
Yeah.
And it's so easy that you're worried that something's wrong.
Yeah, but it's more operational than that. So
Okay.
that's true. I mean, I'm trying to situate it in the whole.
So
the whole commitment to separate syntax from semantics philosophy. But I'm also trying to think how does it get implemented in something like we have CatLab, where we have a syntax category and we map it into some semantic domain.
I haven't really talked much about operads, or multi-categories or any of that sort of stuff. But like the objects of my operad, in this case, if you don't know what an operad is, just follow like loosely, let the words wash over you, kind of thing. But that's usually not what we do here. But operad is like a machine or a way of composing things. And the operad here has as its objects, it's also called a multi-category, all possible, like in P outs, like all possible, B, C, for all possible sets and combinations, et cetera, et cetera.
There's an operad.
There's definitely an operad. Or easier,
Goal.
this would just be ob poly. What am I even talking about? Much easier than what I'm saying. Ob poly is an operad, or is the objects of an operad. And the morphisms, this is just actually, Hom in this polynomial. I'm just going to say something kind of dumb. O from like P1, what are the wiring diagrams or maps from P1 to Q? It's just going to be polymaps from P1 tensor. So this is, I think it's called the endomorphism operad, but it's like, given poly as a monoidal category, this is just the thing you would think to do.
Right.
And so we have this multi-category here, and then we need a functor from O to set that tells us how to fill in the bubbles. So this is like the dynamics itself, and it sends P to the set of pairs S, phi, where S is a set and phi is a coalgebra, either sy to the s to the p to p or s to p of s, whichever one you like better. And this is a set. I mean, it's like a gigantic set. Maybe you want this to be sets of cardinality less than the reals or something.
Right.
But whatever. And then this formula tells you how to, if I have a map from P1 tensor Pn to Q, and I have, S1 y to the S1 mapping to P1 by phi 1, and all these other things, phi n, Sn y to the Sn mapping to Pn, then somehow I need an S and a phi that gives me where sy to the s maps to Q. And so what we do is we take psi and we do psi composed phi 1 tensor phi n. And I know this was too fast, but if you know operads a little bit, then this is what you're seeing here is what we wrote over here, but like organized in the sense of operads.
I can almost hear Sophie's voice with that.
I can almost hear a lot of phone noises. Can you? Thank you.
That is awesome.
Okay, great.
It's going wild.
Great.
Thank you.
Yeah.
Question or comment maybe is that it's not what you described are not the objects of it's a very small subset, right? Just monomial.
Well, yeah, so you could fix this to just be the monomials if you wanted to. That's a great thing to do. You could make these just the wiring diagrams in the sense yesterday. But whatever you do, you're going to be able to make this in algebra, and it's the one we're wanting. Yeah. Okay.
Okay. So thank you.
Sure. Okay. Yeah. Today, I wanted to talk about monoidal structures on Poly and what they do for you. So we already have. Well, any questions before we move on to this subject? Yeah.
One quick question. Yeah, I kind of confused. There's two p here. So in p in the dynam. So no, then yeah. So here is a p and also has phi mapped to p. I'm kind of confused over what this two p is. So there's.
You're saying you're confused about this line? You're confused about this, right?
I confused about the two meaning of the two p here.
Okay.
The basic
What
part
I'm
I
saying,
understand.
so to give a functor from O to set, I tell you what it does on objects of O and on morphisms of O. For each object of O, I'm supposed to give you a set, and for each morphism of O, I'm supposed to give you a function. But
Okay,
you're
so
interested in what I'm doing on objects. So dyn of P is equal to this set, and dyn of psi is somehow represented by this.
Oh, I see.
Yeah.
So p is an object.
Yeah. I'm happy to go over this in like question time, but I'm not focusing on this much. And you're happy to, I'm happy to answer questions, but I'll mainly prefer to talk about this in question time, just because it's not something we're not really focusing on operads themselves. Okay, any questions about anything else before we go to monoidal structures? Okay, so a monoidal structure on Poly is like two things. It would be some kind of special object in Poly. One is the one object category. So it would be one polynomial and a map from Poly times Poly to Poly that we would call like dot or something. Okay. And they would satisfy some laws. So we would have things like I dot P is P dot I, and P1 dot O dot P2, O dot P3 has to be isomorphic to P1, O dot P2, O dot P3. And these isomorphisms can't be crazy. They have to kind of work right even if you had 4 or 5 P's. So many of you already know what a monoidal structure is. Hopefully everybody either knew before they came in or came to day 0. But does anyone know any monoidal structures on Poly?
Plus.
Examples. Okay. What is the 0? What is the I mean, for plus?
The I is the 0 polynomial.
Yeah. So we can add polynomials. And P1 plus 0 is P1. Okay, what else is there?
There's 1 and times.
Yep. P1 times P2.
And then parallel product.
Okay, what's the monoidal unit?
Is it also 1?
1 tensor. So is it true that 1 tensor P is P?
It's actually y.
Well, is this true though?
Oh.
Also? Is 1 also a unit? So what is 1 tensor y?
No, because the exponents will be zeroed out.
Yeah, this is y to the 0.
Oh.
Yeah.
And so multiplies and
You have to
kills
solve.
everything. So this one is y.
So I had a question about that actually for like with regards to the box picture and like constant functors, like constant
Mhm.
polynomials. So what's the corresponding box for that? Because that would be like a constant polynomial would be like an error or a termination state for that.
Yeah, you'd have a box that output like a term of type empty or something.
Okay.
Yeah,
Which would be
but
like
we haven't done, so
halt.
yeah, we didn't really do pictures where like if you have a y to the b plus a prime y to the b prime, that would be like a box that sometimes the state inside of it was telling it to bring in b's and put out a's, and sometimes the state inside of it was telling it to bring in b primes and spit out a primes. And those are hard to draw because they're just kind of switching constantly. Does that make sense?
Yeah.
Sometimes your eyes are closed, sometimes your eyes are open. Sometimes you extend a hand and sometimes you don't. And so if you had an sy to the s to this, we kind of talked about this. And if it went to y plus 1, then this box would be somehow like sometimes spitting out like something of type empty.
Right. Like sometimes it's saying like continue, and sometimes it says like nope.
Yeah.
We're over.
Yep. And tensor, yeah. And when your only tool is tensor, which it has been so far, once one box in the whole system spits out one of those errors, it turns the whole system off and it just stops there and waits for all time. When we start using times, if we use times, I don't know how much we'll get to that, but we might, then we can come and pick up those error states. Okay.
There's more. Much more.
Composition.
What is this one? Oh, y tensor p is p. Okay, what was this next one?
Composition product.
Yeah, we haven't gotten to that yet,
Yeah.
so maybe we should.
Y.
And this one is not symmetric.
Not
And there are more too. The most useful one I've found that isn't these is why am I blanking? Yeah, so I think it's 0 v, which is like, so this one is p v q is p plus p tensor q plus q. This one has, I've found uses for this, like pretty important uses for this one, or important to me uses for this one.
Huh?
Really?
It's like these.
Yeah.
but-
Yeah, somebody, in Haskell you might call this these. Yep. Right, in fact, so there are many, many more also, but these are some good ones. So I wanted to talk about, so tomorrow we'll spend, like day 3 and day 4, Thursday and Friday, we'll spend all on this one. It's like the richest one, the most surprising one in some ways. Today I just wanted to concentrate on these 3. And maybe some of them are closed. They have what's like an internal HOM, and those are interesting too. So let's do that.
Is there like a good intuition for closedness as like, does it match well with iteration? Like how
No, closedness is not about iteration. It's about like internal HOM.
Yeah.
So it's more like currying.
Right. But it just seems very, seems very coincidental that summing a bunch of times gives you the product.
That's just a coincidence.
Okay.
Yeah. Summing a bunch of times gives you the product. In sets, yeah, multiplying a bunch of times gives you the closure, but you can't do bunch of times. Bunch of times is very set-y. Like how many times? 6 or something. So like, yeah. Okay. Right. So what would be a mono? So do you guys, so what is a monoid? If CI tensor is a monoidal category, a monoid is, does anyone know what a monoid or a comonoid is? In that structure? So the people who are here day 0, we talked about it. If you have a monoidal category, you can talk about a monoid in or with respect to it. Yeah. And so what it is it's a triple. Let's call it M, E, star, where M is an object of C. E is a map from, any guesses?
Terminal object.
Nope, we don't have a terminal object.
Nope.
From I, yep. I could be the terminal object. We don't know, I guess. Okay. To M and star. M times M. Any objections?
Or tensor M.
There you go. Great. And then these have to set. Dot. Thank you. Okay, and then, and what do they have to satisfy?
Unitality.
Yeah, and to write unitality, what you do is you say, if I had an M, I could get an I in M. At which point I could do E dot the identity on M. I always write my object name as its own identity. So the identity on M is M. It just makes formulas look nice, and it very often has good properties to do that. So this would go to M tensor M, and then I could star it and get to M, and I want this diagram to commute. It's kind of saying that anything times E. See, if you see what's happening here, E is being on the left of this thing, and whatever thing we've stuck in for M is being on the right. And we're saying that if we just kind of stick E on for free, because we can, then and we times, we get back where we started. So you could write, somebody might want to write this as like M E dot E star M equals M. And similarly, we could write M dot I, and then to M dot E, M dot M, and then star it. And this is saying that M star E is M. These are kind of in quotes. Like that's what this is saying. Right. Okay. Yeah.
Do you think string diagrams will be helpful?
Some people like string diagrams. So this one looks like M, and this one looks like, this one's E, and this one's star. And this one says, and there's another one here too that talks about what happens when you have M O dot M O dot M. Sorry, I'm kind of on 2 places at once now for some reason. I think because I didn't know what to do with my board work. Okay, so we could star, we could copy the first one and star the second two, or we could star the first two and copy the third one, and this commutes. And the three string diagrams we have are that this equals this, and that's the first one, and the second one says that this equals this. And the way you're supposed to read this is like, oh, bubbles are never going, like, I don't have to really care about the bubbles because this is kind of as though I have like a three-way bubble or a four-way bubble, and I won't care how I organize what's inside of here, whether you can organize it with two-area bubbles if you need to, but you don't need to. Yeah?
There was some intuition you emphasized in 7 sketches about somehow the unit like always being there. It's like in the ether, so you don't have to worry about like pulling out of nowhere and then like multiplying by it. Is that kind of
I think so.
also here?
Yeah, I think so. It's just that in 7 sketches, when I said that, like where we said that the identity was kind of in the ether, we were living in a world with just one monoidal product, and that one was just in the ether. But if you have tons of monoidal products, like which one's actually in the ether? You know, which one's actually always there?
Cool.
Like, yeah, okay.
And this map from I to M, is that like when that's instead of I, when it's the terminal product that's out of it, it's like, oh, it identifies an element of M that serves as the identity. But here you've got this I thing, which is just something in the category.
Well, it's something in the category, but it's something that works very well with tensor. This I is just something, but it's pretty special once you've got tensor around.
Yeah, so like for tensor, it'd be a map out of
Y. Yeah.
This would be like a special polymap.
Yeah. It would pick a position. Yeah.
Okay.
Yeah.
Thank you.
Sure. Okay, what's a comonoid? Well, it's a monoid in this thing op, which just means that let's see. I guess I'll call it, I don't know. I guess I'll call it E again. But this time it goes from M to I. I guess sometimes we call this epsilon, and then delta goes from M to M dot M. And I know the notation is a little different, but the reason is because I don't know. Yeah. Okay, and then everything's like almost exactly the same. It's like we have M dot I, but now we're receiving from M dot M, and we're going to M. Everything's just reversed. Because here we know how to do M O dot epsilon and diagonal, or epsilon O dot M and diagonal, and those should commute. And similarly, this diagram just goes up instead of down. Yeah, questions?
Well, you have all this intuition that you've built in other places about like monoidal categories, combining things like, you know, doing cooking and making a lemon meringue pie and that sort of thing. And others have emphasized those too.
Yep.
Could you give 1 or 2 examples of like a comonoid?
Yeah, let's do an in poly.
Okay,
Yeah, we'll give a lot of examples of comonoids and monoids.
thank you.
Sure.
Are the string diagram pictures for comonoids just
Upside down.
Upside down?
Yeah.
I have a question about too the symbols for the equality and isomorphism there. The equality is not an arrow.
It's the identity. If I write equality like this, I'm writing the identity arrow.
Okay.
Sometimes I'm writing an isomorphism that everyone knows, like a canonical isomorphism. But yeah, is that okay?
Yeah, but could you also have written those diagrams as like two triangles that meet?
Yes, you could also have written this as two triangles that meet.
And the isomorphism that is a proper arrow, but it's going to be the obvious one in that circumstance.
I could have written this one like that, yeah.
What's the one on the right?
This thing,
Or one left from that.
this thing.
Yeah.
This says if you have a comonoid, and you take your m and you duplicate, and then you duplicate the right one, it's the same thing as duplicating and then duplicating the left one. It's kind of like if you copy something and get 2 copies, then you copy the second one, now you have 3 copies. But if you copied the first one, now you have 3 copies also, and those 3 copies will be the same, because the 2 things you had were just copies to begin with. Okay.
Is there a name for that?
Co-associativity. And these will ensure that no matter how many times you copy, you copy 43 times, and it doesn't matter how. 44, yeah, 44 also works. Yeah. Okay. So let's talk about monoids and comonoids in poly 0 plus. So a monoid in poly 0 plus would be a polynomial, and then a map from 0 to the polynomial, because 0 is the monoidal unit, and a map from p plus p to p. Okay, so can anyone think of one of these?
There's just the trivial.
So there's only one way to choose this one. I write exclamation point when there's only one map there.
Yeah.
The name of the one map will be called bang or exclamation point. Or shriek. This one? Does anyone know a map from p plus p to p? Yeah, because it's the coproduct, there's a good one. There's a unique one that sends p to p by identity and p to p by identity. But there could be other ones too, as far as we know. This one's just some thing called times or whatever. But the laws tell us that if we go from p into p plus p, maybe I should write it in the same order, p to p plus p, p to 0 plus p, and then to p plus p by bang plus p, and then whatever our special weird map is here, that we get the identity. So it says if we go into the right factor or into the left factor, and we add 0 on the other side, or we star with 0, then we get back where we started from. In other words, when we go in here and go around, what is this saying? This is saying p goes into p plus p, and p plus p goes here, and this is identity. And p goes into the other side, and that composition is identity. Does anyone know what's going on? I'm trying to say that if you want to give me a monoid in this monoidal category, what is it? What do you know about it? I'm starting with a dumb example because there's going to be nothing going on here. It's going to be like very disappointing. Yeah, Nate.
Can I say something that I think you may erupt in uproarious laughter.
That's fun. Okay, yeah.
But it's always something I'm struggling with when I see something like this.
Yeah.
So when you have p plus p to p,
Yeah.
or particularly with comonoids where you get like p to p plus p
Yeah.
on the right-hand side, I'm just going to put it as baldly as I can. Is it the same p?
It's the same p.
It's not just any old polynomial.
Right. If I write p more than once, I'm talking about the same polynomial.
Yeah.
Yeah.
Yeah, and I think the reason is because we often will have, you know, a goes to a plus a where it's some element of a, and it you know, if we have that in set, right?
Yeah.
Like, it wouldn't necessarily be the same element of a.
Well, this is the type signature. These are sets.
Right.
If I actually had a little a in here, it could go to
Correct.
like a prime
Correct. Yeah.
or
which
whatever,
maps to-
whatever in left. Yeah.
Yeah, it's just.
It's hard to tell if the P is uppercase or lowercase.
You guys maybe only pick lowercases.
What?
You guys asked yesterday very, very insistently that I only use lowercase
Fair.
p's. So I'm conforming to that.
Thank you.
Yeah, you're welcome. You're welcome.
Okay, so it's the same P.
It's the same p. Yep.
It's the same old P, and so.
Yep. So what this is saying is that if you go in here by sending this into the right or left half, and the other half you just kind of use the initial object, then this law is telling you that when you use this operation, you're supposed to get back where you started from in either of these two cases. But this is the coproduct. So if this is the coproduct,
Yeah.
then the universal property says this has to be the fold map, the thing that sends. There's only one map like this that does this and this. And there's no data on here. It has to send positions of this to themselves and positions of this to themselves and directions back where they started. So this is the fold map, PP, identity on P. I would usually write just identity. I would usually just write PP. Identity on P, identity on P. And some people might put those in square brackets, but
Either identity.
identity.
What is the bang?
Bang means there's a unique one like this. I allow myself to write bang as the name of a map when there's, or as the name of an element of a set when that set has one element. Yeah. Okay. So what I'm saying is,
Yeah.
every polynomial P has a unique zero plus monoid structure. There's no data in that. It's like you can define it. You can define this. This works in any monoidal category. You can talk about a monoid object. But in this one, it's dumb, and we get nothing interesting. Every polynomial has a unique plus structure, plus monoid structure, and therefore you just don't care, and you never use it again. The only thing you care about is knowing that you've looked here, and there's nothing here. You went to the mine, you opened it up, you explored, and there was nothing in the mine. If we're looking for interesting things, we now know that there is nothing interesting about plus monoids. And plus comonoids, I don't know, they're very interesting. A plus comonoid would be a polynomial and a map to 0, plus some other stuff. So what polynomials map to 0? Well, every position here needs a position here. So the only one is so if P like epsilon delta is a 0 plus comonoid, then P is very interesting. Well, or it's very boring. It's like 0.
Yeah.
So it's like very particular. There's just one of them.
Yeah.
And then there's a map from 0 to 0 and 0 to 0 plus 0, and everybody's bored again. So now I've shown you the most boring one.
I'm sorry, could
Yeah.
you explain what the top one is boring?
It's boring because every polynomial has a unique plus monoid structure. Like for any monoidal category,
Yeah.
I can say a blah monoid or a blah comonoid.
Yeah.
So I could talk about blah monoids.
Yeah.
What? I can talk about plus monoids.
Yeah.
In any category with coproducts,
Yeah.
I can talk about plus monoids.
Mhm.
And those will always be boring. They will always be exactly the objects in the category. Like every object is the carrier for a unique for a plus monoid in exactly one way. You're required to make the map from 0 to p be the unique one, and you're required by the laws to make this one be the fold, the universal property of coproduct.
I'm sorry, I'm just not following.
Sorry.
The fold thing.
Yep. Go ahead.
Can you explain that p plus p goes to p with IDP?
What map is this? Right.
Yeah.
So if you have a category with coproducts, if C has coproducts, like Poly does, then if you have a map from A to X and from B to X, and this one's called phi, and this one's called psi, then you get a map from A plus B to X, and it would be called like phi comma psi.
Right.
Okay, well, what if A, B, and X were all the same? And this was identity, and this was identity. Then, well, identity is the name of a map from A to A. And it's a very good one. It's like it's like I either had an A labeled 1 or an A labeled 2, and either way I get an A. Like I have a tagged union of A and A, but I can throw away the tag if I want to.
In programming, we think of this as like handling both cases.
Yeah.
It's like, yeah.
So, I'm sorry, David, when you write ID comma ID over that arrow from
Yeah.
A plus A to A,
Yeah.
so that looks to me like two functions, doesn't it? Doesn't it produce an A plus an A, or a pair of AA or something?
Or
Well-
it would be ID plus ID.
Yeah.
No, it's definitely not ID plus ID.
Oh, it's not.
No.
You need the two functions. It's the data of that arrow is two functions.
Yeah, if I have phi and psi,
It's the co-product of the two identities.
I send them to
Yeah, that's what I'm struggling with.
psi.
Maybe too much different things.
What are you struggling with?
So-
The notation?
So I'm struggling with why, like,
Why-
how that could be ID, yeah, that arrow could
Well,
be,
let's look at this one.
okay,
Do you agree that if I had an arrow from A to X and an arrow from B to X,
yeah,
then I would get an arrow from the coproduct?
yeah, I emphatically agree.
And do you mind if I call it phi comma psi?
I would not object. in the least.
Okay, then let A, B, and X all be the same. Let phi and psi be identities, and you get the notation that I used.
So it has
That's
a
good.
choice, okay.
You agreed here, and I just specialized, so you have to agree. But
Yeah.
something is getting in the way?
Yeah, so basically it's gonna figure out which side, is it in left or
Yeah.
right?
Yeah.
And give you the one, and in this case, it has the essence of freedom, and it can choose either one and still get the same A.
Yeah. Somehow I need a map from,
Yeah, okay.
I have this, and I union these together,
Yeah,
and I just need a map from this to here, and yeah, you just use the one that sends, both of these to here, and both of these to here, and both of these to here.
That's what I missed.
That's what you needed. Okay.
yeah, that's the thing of beauty
Yep.
and a joy forever.
Okay.
Okay, could
I-
you not destroy it?
Really? Okay. Okay. Yep. I'm gonna get rid of that picture
But I
soon,
guess
though.
it
Yeah.
wasn't obvious to
Oh,
me.
you are gonna get rid of it?
Ah.
Yeah,
ID,
well, no, David, you can
I'll-
erase it.
no, it's okay.
I wanna memorialize it for the class.
Okay.
I got it.
It's an emblem of delight.
Okay.
And so, David, is that upper one, is it basically like, it's boring, cause there's like nothing going on? It's
There's
just
nothing
like
going on. It's
every
everything's
polynomial
forced.
is just
Every-
trivially-
Every polynomial is just trivially a plus monoid.
and by doing more
And that's
more
true
of
in
it, you get the same thing.
I mean, it's interesting. It's nice to be able to do this. If you care about this and you're like, I want to be able to fold things and whatever, like it's nice, yeah. But everything's trivially
Yeah,
a plus monoid, yeah. You might use this monoid map all the time. You might, in programming, maybe it's like your favorite thing in the world, but it's still trivial once you have plus.
Boring because it's easy.
It's boring because it's easy, yeah. And this one's like boring because it's like almost never happens. You almost never have a plus comonoid. Yeah, in Poly, because nothing likes to map into 0.
It's easy for most people.
You have a question?
Can you please say why the unit law holds? Like how, by the universal property? Like why does the square commute?
If you take a position here and you send it to that position, and then you send it to that position in this thing, and then you send it, it'll go to this itself. And then if you have a direction, it'll go back where it started, back where it started, back where it started. I mean, this is true in any monoidal category. Any co-Cartesian monoidal category. There's nothing happening in a plus monoid, but in the poly case, it's easy to, yeah.
I have a question.
Yeah.
So is the way that the plus monoids in poly, the fact like that every
Polynomial
polynomial has a
Unique.
monoid is
monoid structure, yep.
it's the same as like how in set every set has a unique comonoid?
Yes. Yeah, so let's do monoids in poly 1 times. I mean, actually, I kind of feel like we should do Y tensor first, because you guys are more used to tensor, and then we'll go the other one later. These are called, in functional programming, these would be called applicatives, or polynomial applicatives. These are, what is one? It's a polynomial P, a map from P, tensor P to P, and a map from Y to P. I'll do it in the same order. Y to P, and P tensor P to P. Okay. And Nelson and I wrote a paper where we didn't know that these were called applicatives at the time, but we called them collectives. And these are like, if you have a bunch of things working, there's like some kind of there's some kind of feeling that these things are working together. So so let's just examine what these things are, because this one's boring, and this one's going to be interesting. There's lots of interesting examples of this. Yeah. Okay, so so what's happening in this guy here? It's saying if I have a position of P, I was going to write a capital P there. If I have a position of P and another position of P, I1 and I2, I can like aggregate them. Maybe I'm going to call this phi or something instead. So phi1 of I1, I2 is a position of P, So you're able to take, how do I want to say this? What I want to say is there's a lax monoidal functor, like there is a lax monoidal functor poly to set that sends every polynomial to P of 1. And the lax monoidal functors send monoids to monoids. This sends tensor to times. And I feel like everyone's getting lost. Send monoids to monoids. And sorry, I'm going to recover soon. What I'm saying is P of 1 will automatically be a monoid. If you take your polynomial, and it is an applicative, or it has this structure, it's a monoid in this thing, then the positions of it will be a monoid. We'll be able to take two positions and aggregate them. And the highbrow definite reason is because there's plugging in 1 into a polynomial is a lax monoidal functor. So if you like feel highbrow today or later, you could go look at that and see that lax monoidal functors send monoids to monoids. So we know that P of 1 is going to be a monoid. We don't have to check anything. So what that says is we have these two machines, and like if we take their outputs, we can somehow combine them to get 1. So the picture is going to be like we can take any number of P machines, and we can combine their outputs and like aggregate them. So this picture I'm drawing here is in a little thought bubble. because it's not like a wiring diagram like we would normally have. And you can take inputs and use the picture is kind of interesting, but the picture hopefully will make sense. You can use the outputs to decide how they get their next input. So let's try to give what I probably need to do is give you an example of one of these things. Okay, so let's let P be r greater than or equal to 0.
The promise you made yesterday, you said that you could merge wires if you had a monoidal structure.
Yeah.
And now you're doing it.
Yeah.
Okay.
Let me do a different one.
But it's not just about having the monoidal structure. You need those particular polynomials. You need their types to be.
So this whole thing will be type P also. So what it means is you can take any number of P machines and get another P machine, and you can kind of form swarms or like you can pack them together somehow. Okay, so what is this polynomial? 0r. So this polynomial outputs positions, it outputs real numbers, and it inputs a number between, it inputs an x, a real number, such that 0 is less than x is less than r. So you've got this machine. It's outputting. Somebody comes to the party and they give $7. And somebody else comes to the party and they give $12.50. And from there, we get $19.50. So that's on positions. Given a real and another real, we can combine them under a monoid operation. We could have maybe multiplied them, but I'm adding them. Okay. And then, so we're going to call these things contributions. In all of these, in the collectives paper, we called these things contributions and these returns. So you've got this economic collective or bunch of people. All the people have type P, polynomial P. And they can contribute to the space, and then things get returned to them. So here, each one is contributing some money, say 7. And the money is going up this little column. So the first one gives $7, and the second one gives $12.50. And the total contribution is $19.50. And then we get a return here. Someone gives us some money. They give us a number between 0 and $19.50. We get some of our money back for some reason. So we get this much back. Maybe we get 16 back. So where does, on directions, we need, for this direction, 16, to go back to 2 directions here. A direction for this one and a direction for this one. And the direction goes to, in this collective, it goes to 7 and 9. Like this one gets all of its money back, and this one gets the rest back. Whereas if you'd picked like 6 would have gone to, any guesses? 6 and 0. Yeah. So this will be an applicative, or a monoid, a tensor monoid. It'll always feel like you've got these things, they're all contributing to something. Then so all these things contribute some money, and then something comes back in, and it's distributed according to how they contributed in the first place.
Sorry, I answered that, but I'm very lost.
Okay. Is anyone less lost?
I don't understand why it's ordered like this.
Right. This is a not all monoids are commutative. This is not a commutative monoid. You've got a bunch of, you have priority. The first one gets priority, second one gets, so if you had 3 of them contributing, and they did 7, $12.50, and 1, and you got $20 back, this one would get their full 7, this one would get their full $12.50, and this one would get 50 cents of theirs. Like it's just, there's a priority list in this thing. Let's do another one where it's not. Maybe that'll make you feel happier. This is it's a pyramid scheme, but it's fair in the sense that when you come into this pyramid scheme, when you walk into this collective, everyone knows whoever puts their money down first gets their money back first. There's like the lawyers get their money first. I think that's actually true. The lawyers will always get their money first, yeah.
I was just going to say, one of the projects being considered by my group involves this.
Oh, cool.
Actually,
Okay.
Quite interested in that.
Great.
If that's.
Well, yeah, I mean, we can talk, yeah,
I think I'm found enough to ask a question.
okay.
Which is, it feels like you only got to do this because the reals are a monoid in set.
I'm always going to have to put a monoid in my positions. That's true.
Okay.
Yep.
So does that mean that
yeah.
to have a monoid in poly Y tensor,
To have a monoid in poly Y tensor,
you need a carrier polynomial P
you need a carrier polynomial P
whose positions are a monoid.
whose positions are a monoid. Yep.
That's it?
Nope. You also need to be able to take your directions and take how the various things decided what to contribute and distribute your returns accordingly. Maybe I should give you a bunch of simple, I could give you a bunch of simple ones.
Wait,
Yeah.
just to clarify for this behavior.
There's a bunch more, yeah, sorry, yeah.
Is the behavior of the like filling up first, like the prioritization, is that what the behavior that is induced by having to conform to the monoid laws for this particular polynomial for this set?
Oh, I think the
Or
question
is
is,
that just a particular example?
this is just a particular example that shows like
Okay.
how weird and interesting this
So
is.
you could just choose.
There are other ones.
There are
for that
tons of,
polynomial, yeah.
there are probably other ones for this polynomial. There's probably infinitely many, but I don't know that I could think of any.
Yeah.
Yeah.
You could distribute it proportionally, for example.
Let's do one where you could distribute it proportionally. I would like to just write, wait, what am I doing here? Let me just do this. So this is my new polynomial, P. Hopefully I can give you a monoid structure on this. Oh, no, I do need that last one. Okay, y plus. Okay. So I need a map from y to p. I don't think I told you that last time. But the map from y to p I'm going to use is just 0 over here. Because I need something where if somebody contributes 0, and then the other person contributes anything, then all the money flows back to the second one.
Yeah.
Or vice versa. So
Because
0 is a unit here.
Got it. And because the return map in this actually keeps track of the individual contributions.
Yeah,
at the
these
start of
almost
it, so
all-
it can't return more than you contributed at the beginning because that's the direction that's
Yeah,
available. for
that's
the
right.
person.
That's right. Yeah. Yeah. It keeps track. The total amount you could return to this person is dictated to be as much as they gave at most. You can only give as, because that's what I said the directions were, was you give an amount and I'll give you back some of your security deposit or whatever. I'll give you back some of it. Right? I have to give you a number less than or equal to r.
For this setup.
For this setup here.
Yeah,
Yeah.
because in other uses
In other
of
ones,
polys,
yeah.
you have more like prediction markets. You can
Yeah.
make the larger set.
Is that distribution random? Like when you get 16, you said like 7 and 9?
No.
Like,
No, 16, this one, the water flowed up to 7, and then this one, it flowed up 12.50 more. And then someone gave us our security deposit back. They gave us $16 back. And Alice got her full amount back, and Bob got the rest. 16 is 7 plus 9.
why did Alice got 7 and
Because-
not lesser?
Because in this collective, the way it works is it fills up this thing, and the first person gets all.
That's just a choice that you made of
This
the
is
return function.
this is a choice of structure of a monoid structure on P.
Okay.
You could make it go the other way, where the last person gets their money back, but you have to do it in a way that's consistent and associative. So yeah, you would either have to do first in gets their money back first, or last in gets their money back
It's
first.
not a unique thing.
There may be many monoid structures on the same polynomial. I don't know any other ones on this one that I know of. My storage system may know them, but I don't know them right now. Yeah.
So when you use the term carrier here,
Yeah, in general, the carrier is the object. And then this is the unit, and this is the multiplication.
and so like for that case that you just pointed to, the carrier is a particular polynomial, a very specific polynomial.
In this case that I just pointed to, every polynomial is the carrier of a unique plus monoid. In this one,
Yeah.
it's very interesting to find tensor monoids. Those are weird and cool. This one, they're just automatic. Every polynomial carries a unique monoid structure. In this one, they're quite interesting.
Sorry, I thought tensor, are you using tensor? Oh, you're using tensor in the poly sense.
Yeah, in the poly sense, tensor monoids
being
are
run
interesting.
things in parallel.
Yeah, the reason they're called applicatives
Yep.
is that P,
Yep.
P of A times P of B, I don't know if this is going to be interesting, but always maps in like a universal way to P tensor Q of A times B. And so if P was an applicative, then P of A times P of B would map to P tensor P of A times B.
Sorry, are those set maps or are those polymaps?
P of A times I don't know. Maybe I shouldn't be saying. What I'm saying is that if P is an applicative, these are all set maps or polymaps. Every set map is a polymap. But yeah, these are set maps.
Right.
If P has a tensor, yeah, I probably shouldn't be saying this right now, but tensor is what's called the deconvolution of product, which means that, sounds fancy, but all it means is that if you have P of A and a Q of B, you get a P tensor Q of A times B. We could talk about that some other time if we have time. But this is what makes it so that if P was a tensor monoid, then we could just take this line and copy it, but use the fact that P is a tensor monoid to turn the P tensor P into a P. And so now we get what's called a lax monoidal functor, that P is lax monoidal. It has P of A and a P of B gives you a P of A times B.
Right.
And that's how Bartosz Milewski described applicatives in Haskell as lax monoidal functors.
Yeah.
Okay, but that's all kind of aside. What we want to do now is like give just a bunch of examples. And so so suppose we need a map from P tensor P to P, right? So suppose you have, and what it's going to do to this thing is going to treat it as the identity. So I'm not even going to tell you what happens for, if this is y, then we're just going to get identity. And if this is y, we're just going to get identity. So the interesting thing here is that we have two real numbers that are at least 0. What should we send them to? Well, maybe you don't know because I haven't told you. I'm going to send them to R1 plus R2. And then someone gives us a direction, x, and I'm going to send it to, I need to send it to two directions. And so I'll send it to R1x over R1 plus R2 and R2x over R1 plus R2. Okay, so this is probably, so this first guy gives $5, second guy gives $10. And the output is we get $15.
Yep.
And then we get like a $60 return on our investment. Then we get 5 times 60 over 15, which is a third of 60, is returned to the first guy. And 10 times 60, which is 600 over 15, which is 40, 2/3 is returned to the second guy. So this is an applicative. It's just proportional. And the reason I had to make 0 special, even though as usual this total thing is a monoid, it's the non-negative reals. It has to be, it's acting like a monoid. If you plugged in this one, you get this one back. But the reason I had to separate it out is because of the annoying case where these are both 0. Then what do you return to each person? You don't, we're just not going to return anything. If everybody just invests 0, then nothing will be, we're guaranteeing nothing gets returned. Yeah.
Just that last P of thing right up there at the, yeah, What's that between those two? Is it
P
P
times,
times,
yeah.
like a star?
No, the product of sets.
Okay.
Yeah.
Thanks.
Okay, any questions about this applicative? Yeah, this monoid, tensor monoid?
One thing you said is that you had to separate them out as opposed to what?
I originally was hoping that this would just be r greater than or equal to 0, y to the r. That's what I originally wrote down when I thought I knew an applicative here. And then we worked it out. And then in the case where they're both 0, something goes weird. You get 0 over 0.
Right.
And I just remember something being annoying.
But in order to get that sum, for that sum to work out like that, don't you need y to be y to the r?
Where?
In the carrier?
Here?
No, on the left. On the left sum end.
This one?
In order to sum, because you're adding, like when you sum them, you're adding something on the base of the exponential, right? Like y plus.
This is a polynomial. Do you agree with that? I've written a polynomial here.
Yeah.
Okay.
Yeah, but if you sum, like in order to sum the positions with the same exponent, you need the exponent to be the same.
Yeah.
Right. So they're different. Those two polynomials are not.
They're not the same. And I originally thought it was that one.
Right.
Because I
Okay.
thought I had the formula in my head.
Mm-hmm.
But then I got annoyed that it's slightly annoying that you can't do when both people contribute 0.
Right.
You really should not be getting a return on your investment.
Right. So if y was raised to the power of r there, then they would be the same.
Yeah.
Then they would be the same, and it wouldn't work. So you need in the case
Yeah.
on the left hand side, you need the input to be 1. On the y, on just the bare
Yeah.
y.
You need the returns to be 1.
Yeah.
Yeah.
Okay. Gotcha.
Okay. What do you guys think? What do you think of tensor monoids? I can give you a whole bunch of other ones. There's a paper called Collectives something that I can just write down a whole bunch of different ones. Should I give you? Do you want more, or do you want a break?
So what intuitive? Oh, go ahead.
Let's try to get some voice. There are different people saying what they might want now. Break, more tensor monoids after a break.
I want you to say something you said before again.
Okay. Say something I said before again.
Yeah, but I wrote it down.
Okay.
To get a monoid in polytensor, you need a polynomial p whose positions are monoid in set, and a way to distribute what you got back.
Yeah.
Yeah.
So I mean, what is the type of this thing? So we have phi1 taking p of 1 times p of 1 to p of 1. And this has to be, and then we also have a map from 1 to p of 1. And together these need to be a monoid in set. But then we also have this thing phi sharp that takes a position of the first one and a position of the second one and a return and takes a return p bracket I1. So let's just call this thing star or something. I1 star I2. Really, I'm writing phi of I1 I2 is star, right? So it takes this return on the combined investments. So all these guys contributed something. And now the world has received them and is giving something back. And so it takes that thing giving back and gives you something of type I1, a direction at I1, and because we're in tensor land, so we need a direction of each, P of I2. So I need a formula that takes this return and distributes it to each thing. And I'm allowed to use what they gave in my decision.
Yeah. Because it was nagging, like scratching at my head, because distributing feels like comonoid.
Yeah, it's kind of comonoid-y coming back. Yeah.
It's like I wanted something clean, like it needs to be a monoid on
Yeah, but it's
position,
not.
and I
It's
thought
allowed.
monoid-
It has more data that it's allowed to use. Yeah.
Yes.
Yeah.
Yes.
And so one way to write this is you could write, it turns out to be often interesting. So I'm going to write this as two maps, one to P of I1 and one to P of I2, right? Because I can always take any map to a product and write it as two.
Yeah.
So I'm going to write the first one
Yeah.
as I1 over I1 star I2, taking P bracket I1. So if someone gives you something of type I1 times I2, we're going to kind of take the proportion that is I1's, and we're going to take the proportion that is I2's. And this notation turns out to be kind of nice. Like the laws that we need to satisfy that we've never talked about are going to look like cancellation laws, like with things canceling.
Yes.
So it's kind of a nice notation for that reason. But also note that in this case it literally was.
Yes. Yes.
Like I literally say that the thing called R1 over R1 plus R2 of X is like multiplying.
Yeah.
Yeah.
But in general.
In general, it won't
It's a
literally be
metaphor.
that. In general, it's a metaphor. Yeah. But it will be. It's saying, I want I1's part of
Yeah.
the combined contribution.
And you're saying all tensor
Monoids.
monoids have this flavor.
Yeah.
It comes
Well,
from
sorry.
their-
You look at it and you put this flavor on, and you see if it fits, and then it settles into your mind and it fits. So
Uh-huh.
yeah. Like all math, like yeah.
Yeah.
All applied math has that flavor.
All applied math.
Has the flavor of flavors being applied to math. Of material, of matter and pattern aligning somehow.
Okay.
Find a collective structure, in other words, an applicative structure. In other words, a tensor monoid structure. Those are just synonyms. Collectives is probably the one that's going to go away because it's the newest one and the least used one. But anyway, it's a tensor. Find a tensor monoid structure on this, meaning find a map from my tensor my to my, and from y to my, if m is a monoid. So m is a monoid in set, like the real numbers or whatever. Find a tensor monoid structure on my. Exercise 2. And I'll go over these exercises because I think they're interesting. But we'll just work on them for like 15 minutes or something. For any set, find a tensor monoid structure on y to the s. Number 3, fix a set U, like the set of reals or the set of colors or whatever you want, and make a polynomial whose positions are subsets of U. So the people are going to be contributing subsets. They have all their, like this one contributes salt and pepper, this one contributes, some steak or whatever. And then you get back a subset of what you contributed for whatever reason. That's a collective. So everybody's contributing, and then something's returned, a subset of the combined thing is returned, and you have to distribute it. Okay, so find tensor monoid structures on all these. In other words, just see if you can make one up. Do you guys think you can do this? Like you can try, or do you need some help? I'll be walking around. Okay, this one says, if C is a category with coproducts, then I can make a tensor monoid structure where the contributions, what people offer, is an object, and what's returned is a map out of that object. This symbol here, C bracket C, means morphisms out of little c. Okay, so you give an object, what you're going to get back. You give an object of C, what you're going to get back is a map out of your object. C has coproducts. You're going to need to be able to combine two objects to get an object, and take an arrow out of the combined thing, and somehow get an arrow out of each of the combined combiners.
Small category?
C is a category, yeah, small category. In this one, what you contribute is a whole vector field. So you have at every point you contribute like a function from R2 to R2. And what you get back is a point. So like 5 people contribute vector fields, all sorts of different weird ways of moving through R2. And your job, then you combine those vector fields somehow. So now you combine your 5 people's weird direction fields, and you get one. Then somebody in the world gives back a point, and your job is to pass back a point to each of the people. You can pick whichever of these exercises you want to do. In this one, P and Q are tensor monoids already. Show that P tensor Q is. Or P and Q are tensor monoids already. Show that P times Q is. Or that P compose Q is, even though we haven't gotten there yet.
That's not a stupid one.
Yeah.
Can I have one?
Yeah.
Mine is, can I erase this?
Yeah.
You have like, so there's some like things and they have like their eyes can be open or shut.
Okay.
So the polynomial I care about, if your eyes are open, then you can receive either like black or white. And if your eyes are closed, then you can't receive anything. Or you receive like, just like the
hum of
constant-
existence.
Yeah, the hum of existence.
Mm-hmm.
So then so then you need like P tensor P to P. What this should do is like, how do you combine 2 of these things into like one big eye?
Yeah.
If one of them is open, if at least one of them is open, then like the big eye is open. And then what gets sent back to like the little guys. So you can sort of think about that. I don't know.
Okay, cool. Great.
Sorry, how does that one relate to tensor monoids?
That this is another
There's a
tensor.
tensor monoid.
Yeah. Sophie's claiming show there's a tensor monoid structure on it.
And these are like show monoid maps, considering these to be the carriers.
Oh.
Those are social tensors.
Okay.
Show
So why don't we work for like till lunch, I guess. Let's just work till lunch, and I'll come around, and we'll, yeah. Find a tensor monoid structure on these things.
Okay, but they're the carriers of those.
These are the carriers, yeah.
Okay.